remember at the end of last lecture, the very last example I did was this rotation. I think it was a rotation through an angle of pi over 3 radians. And so let me just remind you how that went. Right? We had the transformation, and what it does is it takes every point in the plane, rotates it counterclockwise through an angle of pi over 3. And so the picture looked something like this. The way we found the matrix for that transformation is to look at what happens to the standard basis vectors E1 and E2, right? And so what happened, T of E1 was right there. T of E2 is right there by writing down the actual vectors for this one. So this was 1/2 root 3 over 2, and this one over here was negative root 3 over 2 1/2. And so then the standard matrix for this transformation is obtained by just writing down in the first column the entries corresponding to T of E1, and in the second column the entries corresponding to T of E2. So what I want to do is generalize this. So let's say more generally, let's let T be the rotation of the plane counterclockwise. Let's write that down. Rotation of the plane counterclockwise, clockwise through an angle. Let's just call it now theta. And this is, so let's see, rotation of the plane counterclockwise through an angle theta. And here, this is about the origin. Okay, so now the picture is going to look similar. We're rotating about the origin, so every point in the plane gets rotated through an angle of theta. So let's just mark that. Right, there's an angle of theta. And our goal is to find the standard matrix for this transformation right here. We're going to do it exactly the same way as we did this specific problem right here. What we want to do is figure out, identify what happens to the standard basis vector. So if we know what T of E1 and T of E2 are, that tells us everything we need to know. We can write down the matrix for that transformation. And it really just requires us to do a little bit of unit circle trigonometry, right? So E1 lives on the unit circle. T of E1 is going to be, so let's see, well, who's this going to be? Well, that point right there on the unit circle, if we've rotated through an angle of theta, that's going to be cosine of theta sine theta. Right, so E1 gets sent to the column vector cosine theta sine theta. Also E2, so let's see. So if that's an angle of theta right there, then measured from the positive x-axis, this is going to be pi over 2 plus theta. So T of E2 will be sitting right there, and T of E2 is, so it's going to be, well, okay, officially it's cosine of theta plus pi over 2, and sine of theta plus pi over 2. Right, so there's the vector. Now, who is that Well, cosine of pi plus pi over 2, if you remember from your trigonometry, that's the same as negative sine of theta. And sine of theta plus pi over 2, that's the same as cosine of theta. So the standard matrix for a rotation counterclockwise through an angle of pi over 2 when we rotate about the origin. It's a linear transformation. The matrix is, and we're going to give this a symbol. This is what your book uses here, r of theta. R of theta is equal to cosine theta, sine theta in the first column, and minus sine theta, cosine theta in the second column. So there's the standard matrix for that rotation. Okay, so there's our first example of a linear transformation that has been defined geometrically, right? We tell what happens to each vector by describing geometrically what happens to them. There's a couple of other well-known transformations that we can describe geometrically, right? So we've handled the rotations, and we'd like to handle a couple of others. Right, and before I erase this, so I mean, this is one that you want to keep in mind. This, we will come back to this, and you will need to know this one right here. So, right, so this is the rotation matrix. Okay, so the next of the geometric transformations, reflections. And, well, so we'll start off with two-dimensional reflection. So the first one I want to think about. So let's let T be the reflection of the plane R2 about the x-axis. So what does that do? It takes the plane and it takes every single point and flips it about the x-axis. So if you have a point here, x comma y, what happens to it? Well, it gets taken, if you reflect about the x-axis, it gets taken to the point x comma minus y. The x coordinate will stay the same, but the y coordinate will get negated. Now, what we want to do is find the standard matrix corresponding to this transformation. And how do we do that? Well, the same way we've been doing this. We see what happens to the standard basis vectors. So we want to know if E1 and E2 are as marked, right? When you apply T, the reflection about the x-axis, what happens to E1? Well, T of E1, well, nothing happens to E1, right? When you reflect about the x-axis stays put. So T of E1 is the matrix 1, or the vector 1, 0. How about E2? Well, T of E2 gets taken down to here. And so T of E2, it's easy to see, that's equal to the column vector 0, minus 1. And so the matrix corresponding to the reflection about the x-axis, 1, 0, and 0, minus 1. Now, okay, so there's reflection about the x-axis. I want to do a couple more examples in the plane. Reflection about the y-axis, and reflection about the line y equals x. So first, let's just leave this as an exercise. So if we reflect about the y-axis, so let's say find the standard matrix of the reflection about the y-axis. So what would you do? Figure out what happens to the standard basis vectors E1 and E2. Should be easy to write down that matrix. And then let's do one more example of a reflection in R2. What if we reflect about the line y equals x? All right, so imagine taking the plane and flipping it over about that line right there. What happens? Well, what happens when you take any point and flip it about the line y equals x, right? So here's a point, call that x comma y. What happens when you flip it? It ends up over there, the roles of x and y get reversed. Now, to actually write down the matrix, we need to figure out what happens to E1 and E2. Well, I think it should be clear that T of E1 equals E2, which written as a column vector is 0, 1, and T of E2 equals E1, written as a column vector, that's 1, 0. So the standard matrix corresponding to this transformation looks like that. As rows, we get 0, 1, 1, 0. Now, let's take things up one more dimension. You can also reflect R3 about certain planes. So let's now, so here's a picture of R3. And what I want to do is reflect about the XY plane. Right, so you can see here's the XY plane, and what happens if you take any point here, X, Y, Z, and reflect about the plane Y, about the plane Z equals 0. What happens? This point gets taken to a point below the plane, right? And it will be X comma Y comma minus Z. Right, so it's the reflection that takes the point X, Y, Z to the point X, Y minus Z. To find the matrix corresponding to this one, we figure out what happens to the standard basis vectors. Well, now we're in R3, so the standard basis vectors are E1, E2, and E3. All right, so what happens if we call this reflection T of E1? Well, if we're reflecting about the plane, about the XY plane, nothing happens to E1. Stays put. So T of E1 is now 1, 0, 0. T of E2. Well, E2 is also sitting in the XY plane, and so nothing happens to it. And then T of E3, well, E3 gets sent down to its reflected version, negative E3. And so that will be 0, 0, minus 1. So the matrix corresponding to reflection about the XY plane, and I should have labeled this, so this is about, or let's say reflection about the XY plane. The corresponding matrix, column 1 is 1, 0, 0, column 2 is 0, 1, 0, column 3, 0, 0, minus 1. You can also reflect about various planes. In particular, you can reflect about the YZ plane and the XZ plane. And so as exercises, you should write down the matrices for those. And you can see, for the other examples, and for maybe better pictures than I can draw, I'll say see page 85 in the book where it discusses reflections. There's another type of transformation that can be defined geometrically. They're called projections. So projections, and we'll start off once again two-dimensionally. Projection well, we're going to have two different projections. There'll be projection onto the x-axis, projection on the y-axis. So what projection onto the x-axis is, so this will be onto the x-axis. What that does is it takes any point in the plane, x comma y, and it sends it straight down to the point x comma 0. If it was over, if it was below the x-axis, it's still a point xy, and it sends it to the point, let's call it something else, let's call it AB. That will go to the point A comma 0. So it smashes everything straight down or straight up to the x-axis. All right, so that's called projection, sometimes orthogonal projection. So let's see now, if T is the orthogonal projection onto the x-axis, to write down the corresponding matrix, we need to know what happens to E1 and what happens to E2. Well, let's see. So if E1 is right here and E2 is right here, let's see, T of E1, well, nothing happens to E1. Right? If you're sitting here, projection onto the x-axis does nothing. And so there's T of E1. T of E2, now E2 gets taken down onto the origin, and so T of E2 is the vector 0, 0. That means that the matrix corresponding to projection onto the x-axis looks like this. First column 1, 0, second column 0, 0. There's also projection onto the y-axis, so that pushes everything horizontally, smashes everything horizontally onto the y-axis. I'll leave that as an exercise for you. Figure out the matrix for that. We can define projections also, or discuss projections in 3 dimensions. So let's say we want to project onto the xy plane. What does that mean? Well, it would take a point x, y, 0, and it would take it directly down onto the point. Oh, sorry, I said x, y, 0. Just gave away the answer there. X, Y, Z. If we take a point x, y, z, smash it down onto the xy plane, the corresponding point will be x, y, 0. And now that we've been doing this for a while, I think we can maybe just write down the matrix. So let's see, what happens to E1, which would be on the x-axis here. E1, well, nothing happens. That means that T of E1 is the column vector 1, 0, 0. How about E2? That's the point of the vector on the y-axis. E2, nothing happens. How about E3? Well, E3 is right here. It gets projected down to the origin. And so the matrix of the projection onto the xy axis is right there. Smash down. There's the matrix. If you want to see better pictures and more discussion, there's also orthogonal projection onto the xz plane and the yz plane. You should be able to figure out these, but you could also see page 86 for more pictures and discussion and computation of all of these matrices. Okay, so that's it for geometric descriptions or for discussion of geometric, I can't say this right, so what am I trying to say? This is geometric discussion of transformations. All right, see you next time.